Hi all. Okay, so today we're going to be looking at the stack, sometimes referred to as the call stack. So before we get to the stack, first we're going to look at just a refresher on program execution on the CPU, so it all should be familiar to you. Then we'll look at the stack as an abstract data construct, a data structure, and then we'll look at specifically at the call stack and what we mean by the call stack. We'll describe what its purpose is and what gets stored on the stack, and then we'll look at the kinds of registers and instructions that influence the stack. Following that, I'll show you how virtual process memory is typically laid out when loading and running programs. Following that, we'll briefly talk on calling conventions, which is the differences between the way different architectures and systems can set up the stack when you call in functions. And finally, I'll look at a demonstration of some of this stuff in GDB. Okay, so when our CPU is running, typically the way it works is it will fetch an instruction from memory and store that in the instruction pointer, which is also known as the program counter sometimes. It's IP or EIP or RIP, depending on if you're working in 16, 32 or 64-bit architectures. So it'll load an instruction into the instruction pointer, then it'll execute it, and then it'll increment the instruction pointer to the next instruction that needs to be run. So in order to do more interesting things with this, we have branching, so like conditional branching, if statements, stuff like that. Basically the way these work are through jump instructions or jumping off, so JMP, JNZ, etc., things like this. So JMP is just an unconditional jump. If you hit that instruction, you're going to jump to wherever the memory location that it's the jump instruction is associated with. You'll jump there every time. With JNZ, this is how you do branches. So it's like it's basically if there's any comparison, there'll be a comparison operation before the jump not 0, and if the result of the comparison operation is not 0, it'll set a special flag in the processor, and then if that flag's set, then it will jump. It won't jump because it's a 0 flag. So yeah, depending. I think there's a jump 0 as well. There's a few others that you can look at. So functions are, as you're probably well aware, the ways that you can like reuse code. So they're also known as subroutines sometimes. And when we call a function, we typically want some temporary state within the function. So we can have things like local variables, and we can use the parameter space that we've passed into the function. And following the function's execution, we then want to return back to where we left off before the function was called. So the stack is a stack in general, abstractly. Well, so the stack. So okay, stacks are first in, last out data structures. So I think stack of plates, stack of papers, something like that. You can either add an element to the top of the stack, or you can take an element from the top of the stack, but you can't like just dip into the middle and start like pulling data out of it. Technically you can if you do like direct memory lookups on the stack, but it's not common. And okay, so here's an example. So let's say we have a stack and we have a register just with some data in it. It's currently got just some garbage data, ASDF, in it. So let's say we move the string B into the EAX register. We can then use the push operation to add an element onto the top of the stack, whatever the contents of EAX are. So in this case it's B. And then we can do the same thing again with C. And then we might continue program execution whilst we're within this C function. We might actually be doing some other operations that actually change the value of the CAX register. So if we want to then get the C back, we can pop that from EAX, and then same again with B. So that's just an example of how stacks work in general. So in practice, it's more complicated than this. There's more than just like one thing getting pushed or popped to the stack, pushed or popped from the stack. So functions and the information that's held about functions, in order to manage like in order to manage typical process execution, you need more information. So the first thing that usually gets pushed onto the stack in a stack frame is the return address. So this is used so that at the end, as I mentioned at the end, you can go back to the next instruction that you needed to that was going to be executed. Following this is the base pointer. So this usually gets set to ESP when the stack frame gets created. So ESP is a pointer which points to the top of the stack. When you first create a stack frame, you push the return address onto the stack, then you push whatever the current the top of the current stack frame is, so that you know where to go back to after. And you can also do interesting IMEX debugging easier, because if you've got a reference to the base pointer from the frame below, and then that frame has a reference to the base pointer from the frame below, you can like easily step down the stack. After that, you push local variables. The space for local variables gets pushed to the stack, and then after that the parameters get pushed to the stack. The order that the parameters get pushed in usually is from right to left, so the furthest right parameter in your function call will get pushed first, and then one to the left, etc. This can vary based on the calling conventions. So what influences the stack? This is useful stuff for when you're actually like analyzing the program and trying to look at how what things can actually be messing around with the values on the stack for you. So the instruction pointer, as we mentioned, it's the program counter instruction pointer. It's the register which contains the next instruction to be run. We've also got the stack pointer, which points to the top of the stack, and the base pointer, which is also known as the frame pointer, depending on which resources you're reading from. That contains the address at the bottom of the stack frame. Actually, it's not. It's slightly off. It's actually the address. Well, so the address is the base pointer below, so it's actually not technically the bottom, but it's used as an offset so that you can calculate things like, so you can access values that are on the stack, like local variables. It's used as like a base point so that you can like do some arithmetic on pointers in order to access different variables. Okay, so instructions. So we've got some instructions help us like manage the stack. So push, actually, the push instruction it'll do two things at once. So it'll first add an element onto the top of the stack, and then it'll expand the stack pointer. So you don't actually have to do these two steps separately. It actually does it for you. And pop does the opposite, where it will remove an element from the top of the stack, and then it'll it'll collapse ESP, so it'll shrink the stack. So we've removed an item. So call will push the return address and update the instruction pointer. Return does the opposite, so it'll pop the return address off and it'll update the instruction pointer. So these are the things that typically influence the stack at runtime. There are other, like I mentioned before, we could directly add or subtract from the ESP, or we could like move data into memory locations addressed by the stack pointer as well. But so these are things to watch out for if you're wondering what's influencing your stack. Okay, so process memory layout. So the typical representation, this picture is a pretty standard representation of process memory layout. So it starts at the high memory addresses and goes down to the low memory addresses. This is something really important to note. So as before, I mentioned that a stack would grow up, a stack builds up on top of each other. As the stack actually starts at the high memory locations, at high memory addresses, the stack will actually grow downwards. So this is a typical thing that people a way that this gets explained conceptually. The heap grows the other way. So they kind of like grow towards each other. So I actually think that this is a kind of a confusing way of thinking about it. I think it's a lot easier to think of as a piece of paper. You don't have to like mentally invert the stack in your head if you just think about memory addresses as like lines on a piece of paper. So you might have like the first line, the second line, the third line. You go down to the bottom, and the stack actually will just grow upwards. Not sure why this is, but it's very why it's explained this way, but it's very common. But yeah, that's something that might help you reason about these things. Okay, so just as a quick one to explain some of the others. So the stack, as we just explained, contains things about the function. The heap is a location where all the data gets stored, that like objects that we create with new or like malloc, and we can free up space there by using free or delete. BSS section contains static variables. It doesn't contain the static variables, sorry, it has the uninitialized static variables, and data is where when they get initialized, that's where it's stored in the data section. And the text is just the code section. Okay. So as I mentioned before, calling conventions are just like slight differences in the way that functions set up. So there can be differences in the order that parameters get put on the stack, or whether registers are used before the stack for like local variables or parameters. And it also can have some variances in who cleans up the stack afterwards. So like after a function has been called, when a function is about to return, does it clean up the stack beforehand, or does the function that called the function clean up after it's finished running? So that can vary sometimes. So an example to just illustrate this is that on Linux and GCC, the difference between the way that 32-bit binaries and 64-bit binaries typically built is the 32-bit binaries just put all the parameters on the stack, and they also put the local variables on the stack. But 64-bit architecture, well, GCC, when you're compiling 64-bit binary, will actually fill like 6 general purpose registers first, and then start using the stack when it runs out of those, to try and like avoid stack corruption. Alright, so I'll give a quick demo.